This conference will now be recorded.
All right, thanks, Sarah. Thanks, Paul. Afternoon, all. Again, as Paul said, the presentation this afternoon is going to be on the performance of reinforced earth wall. This study we did with Tensar. So throughout the presentation, I'm going to be referring to a Tensar solution because that's what we used in the study as our research partner. Well, essentially what we're looking at is the performance of reinforced earth wing wall under high-speed train impact load. A quick overview of the outline of the presentation. I'm going to give an introduction as to why we carried out this research, what the objectives were at the time, and what we hope to achieve through the research. And then going to introduce or present on the methodology of the research, how we went about it, and then the conclusions of the study. And part of that then goes into if we are able to show that we can use reinforced soil structures as part of bridge design for high-speed train or in high-speed train environment, what sort of repair solutions do we have to have in place should we have the unlikely event of a derailment? And then as part of that, again, is to now look at what are the commercial benefits, what are the carbon, benefits of that, how sustainable it is compared to the alternative conventional reinforced concrete structures. And then the summary and then questions from everybody, if there is any. Now, the key objective of this research is to answer, two questions, and the questions were, is Tensar reinforced wing wall a viable solution to accommodate impact loading due to train derailment? And this question came about, I think, about a couple of years ago at the, or a bit earlier than that, at the beginning or around that time, the use of reinforced earth wall, wing wall or abutment wasn't allowed as a viable alternative or a suitable alternative in the design of bridge structures in HS2. So, and the question, one of the questions that needed to be answered for that to be considered suitable was how will this type of structure perform under impact loading? And then we, in conjunction with Tensar, decided to look at a numerical modeling approach to see if we subject a conventional reinforced earth wall, nothing different, just what we would normally use if we were designing that. If we subject it to high-speed train impact load, how would it perform? And the criteria to then demonstrate that it is sufficiently robust is to demonstrate that it satisfies a no collapse criterion, which is a criterion within HS2 technical standard for bridge design. And within that standard, however, there is no clear definition of what a no collapse criterion means. I think as engineers, we all generally know that for structures, we've got different measures in design to check whether or not we are getting close to the ultimate limit state of such structures. And one of those means of checking that is relative rotation, which is defined we went to EC7, the Eurocode for geotechnical design, Annex H. At the back of that particular document is defined as 1/150. As this was a concept design, not a full detailed design position, we decided to adopt a slightly more stringent criterion. So instead of 1/150, we decided to use 1/450 as a check. And if the outcome of the analysis shows that we are within that sort of stringent criterion that we're not going to be looking to refine it any further. But we recognize that 1/450 is actually quite a conservative criterion to use for a portal frame, which essentially what the bridge structure that we were considering was. Now, how did we go about this study? We used an already designed overbridge along the HS2 trace. So this was, we chose a bridge within the C2, C3 section, which is constructed or being constructed by EKFB. So that's a JV between FIH, Kia, BAM, and Ferrovia. And their designer for that section is Arcadis and Cowie. So this particular bridge had been designed as a reinforced concrete bridge with reinforced concrete abutment and wing wall. So this was ideal for the study. And the section that we analyzed in this study is shown in the red box on this slide. Now, the key principle for design for impact loading is in the standard that I introduced earlier, is to avoid impact loads where possible, and where such is not possible is to design for a protection section of the wall. And so there's a protection, and we're going to see it in subsequent slides where I'm going to be referring to protection wing walls and non-protection wing walls. But essentially, this is this slide defines that where you are unable to avoid a collapse, then within a certain distance from the actual bridge structure itself, then you do have a protection zone and a non-protection zone, which is shown on the next slide here for the case study that we considered. So the wing wall immediately adjacent to the bridge abutment is what is defined as the non-protection wing wall here, and the protection wing wall, which is piled. So the abutment is piled, the protection wing wall is also piled, and it's at a 15-degree inclination to the bridge abutment, which is parallel to the track, as you probably can see from this slide here. So the abutment is parallel to the track, and then the protection wing wall is inclined at 15 degrees away from the non-protection wing wall and the abutment. So in the model that we built in 3D FE analysis, you will be seeing all of these various sections defined and referred to throughout the rest of the presentation. So we refer to that, the reinforced concrete option, as option A, which is the initial option. Then option B is now what we trying to compare the performance of is the Tensar reinforced earth wing wall. And this outline that you're seeing here is a standard detail that we would adopt for designing such a reinforced wing wall for any other type of bridge. So there is nothing special over and above the usual Geogrid design for use in a bridge abutment or wing wall. The material properties that we chose for the soil within the wing wall is what we would normally use again for as granular material or granular fill at the back of a structure, which we generally classified as Class 6N or Class 6 FI. And that, what we've got here, friction angle of 36 and material unit weight of 19 to 20, again, is commonly used in such environments. Now, looking at the facing of that structure is, so we've got to have facing panels. So we chose a 1 meter by 1 meter concrete panels, which is 200 mil thick, within the non-protection zone as well as the protection zone. And each of those sections is about 14 meter in length. What the key difference between the option B and option A, as you can see from this slide, is the option B is only got a piled abutment. So the reinforced earth section is not piled, is all on shallow foundation. Now, we're now going to look into how we define the forces that goes into the protection wing wall and the non-protection wing wall. And so the standard says where overbridge supports have been designed assuming a non-collapse criterion. In the event of derailment, then the unprotected support within 25 meters need to be designed for impact force. So the force is dependent on derailment speed and the distance between the supports and the center line of the relevant track. And what that means when we get to this section here is we can see that the further you are away from the center line of the track, the lower the impact force that you would expect on such structures. So the particular structure that we considered here, it's about 14 meters away. So the red line, the red dotted line that you can see here, it's the speed of the design speed of the track. And when you trace along the red dotted line, we are roughly going to be at around 30,000 meganewton at various lengths from the structure. So that is summarized on this page here, the next page, of the load we considered for the protection zone and for the non-protection zone. And the load is applied as a line load at about 1.5 meters above ground level. And the other main difference that you can see from this table is there's about 10% difference in the load that you applied to the protection wing wall and the non-protection wing wall, which again allows us, when defining such load, to take into account how that propagates from the protection wing wall all the way back to the abutment. We decided to use 3D FE analysis in the assessment of the performance of each option. And option A is shown schematically here. You can see the abutment and the piled foundation of the abutment, as well as the non-protection wing wall, which is not piled, and the protection wing wall, which is piled. The diameter of the piles used in all of the areas is 1,200 millimeters, so 1.3 meter diameter piles. Compared to the option B, which is the reinforced structure alternative, again shown schematically here, we can see the piled foundation of the abutment and the wing wall, and the for the protection and the non-protection is not piled. What you probably notice here is that the protection wing wall is not inclined at 15 degrees as shown in the plan that I presented earlier. That's an approximation that we made in the setup of the model, and we did a sensitivity check because it's quicker to set it up like that without that inclination, and that didn't really have any impact on the outcome of the analysis. Now, looking at the result, I expect there may be a little bit more question about the details of the material models. If anybody is interested in that, then I can give a bit more detail on the material models considered, the strength of the properties for the wing walls and for the piles. Can provide that later on. Now, what we have on this slide is now comparing the performance of the piled and the wing wall alternative. Looking at the abutment, bearing in mind the 1/450 acceptance criterion that I presented earlier. So we looked at the relative rotation of the wing wall, and what this is showing is following the application of the impact load of the derailed terrain, we only measure about 1/2000 relative rotation in the wing wall. And so that is, substantially less than what is considered acceptable. So, and that's on the right-hand side, we have the Auri wing wall. On the left-hand side is we have the reinforced concrete wing wall, which, though the number is not shown there, you would expect is substantially less than 1/2000. But the main focus of the research is to check, can we satisfy the 1/450 with the reinforced earth wall alternative? And how does that then propagate from the point of impact all the way to the abutment? So the abutment here is the structure that we're trying to protect. We can see for option A, which is the piled, the reinforced concrete alternative, we've got a relatively contained small area of deformation. So the extent of deformation is only about 10 meters. By the time we get to about 10 meters away from the point of impact, actually, the magnitude of movement is down to roughly around 5 mil. At the point of impact, with the donation here, we've got close to about 100 mil movement immediately at the point of application. But more importantly, that decayed very quickly. By the time we get to the bridge abutment, there is relatively no impact on the abutment. Compared to the reinforced earth wall alternative, the zone of deformation and the zone of damage is substantially bigger. And you would expect that because this is now the difference between the piled foundation option compared to the shallow foundation reinforced earth wall. Now, the crater or the zone of impact is not 10 meters. It's that propagation is as far as about 18 meters away from the point of load impact. And at 18 meters, we're still getting more than 5 mil. We have about 10 mil movement. But more importantly, the zone of damage is substantial at the point of impact. But as we move towards the abutment, which is the bridge structure that we're trying to protect, the dampening effect of the soil reduces the impact very rapidly. That at the bridge abutment, there is relatively low impact on the bridge. And now, one of the things that we're going to see later on is actually the movement of the abutment, the relative movement of the abutment following such impact is less than 1/450, which we consider as an acceptable position to demonstrate no collapse of the bridge structure under such impact load. So for the bridge structure, we can show by the outcome of those analyses and looking at the deformation pattern and the propagation of those deformation all the way to the bridge, that the bridge is not going to collapse. But then we are still left with a damaged wing wall. So this particular slide here indicates that the wing wall is going to be substantially damaged. Now, what does that mean? And how do we assess that in terms of, this is a geogrid reinforced wing wall. Looking at the geogrid element, the area with the stress concentration here, the areas that it's shown that will be substantially damaged, again, not surprisingly, because this is where we apply our impact load. And the other thing that we checked and not presented here is the mobilized strain. So the way Geogrid mobilized resistance is through, it's in response to movement and within a certain strain level. And when the Geogrid elements are stressed or strained beyond a particular limit, then they are no longer going to be able to perform the same function if left in place without replacement. So what this is shown here is the geogrid will be damaged and will be strained beyond their ultimate limit and will need to be replaced. Now, to look at the non-protection zone, because the forces that I've shown so far is been the application of load on the protection wing wall. So the non-protection wing wall is immediately adjacent to the abutment. So we applied 10% reduction in the impact load, which is the way it's been classified in terms of impact loading on the non-protection wing wall, and looked for the same level of performance and propagation of deformation and stresses to the abutment. And what we also showed in the analysis is that the impact of such load and the effect of such load on the bridge abutment is actually substantially less than 1 over 450. So we've got relative rotation of 1 over 21,000 here, which indicates that there will be relatively no impact on the abutment, and we are able to demonstrate that the abutment and the bridge structure is not going to collapse under such impact load. So that leaves us with a conclusion that Geogrid reinforced wing walls is suitable and will not result in the collapse of the structure under the sort of impact loading that we have considered in this study. We recognize that we've taken a case study based on a particular bridge structure and a combination of distance of the load application, so the distance of the abutment to the railway line determines how much load gets applied to the wing walls. So there may be some other structures where the railway line is a bit closer to the wing walls, and where the load application will be different, or where the orientation of the wing wall to the railway line is different to the case study that we've used here, where the outcome of such analysis will be different. But for cases similar to the one that we've considered here, then the outcome is very clear that the bridge is not going to collapse under such impact load. We then need to look at, because the wing wall will no longer be serviceable, or is it still serviceable? Can we repair it? So this is the bit where I'm going to go into next. Now, we've identified that the zone of concentrated damage is, as shown there, which is about approximately 9 meters that will be damaged and will need to be repaired. Tensar have a repair, a standard repair option that can be considered for this. The Geogrid will no longer be able to perform, so they will need to be removed. They will need to be excavated and replaced. The concrete panels, which are the facing to the Geogrid reinforced wing wall, will also need to be replaced. And one of the examples that we've shown here are places where that has been done before, though not in a high-speed train environment, but in a, I think this probably was taken from an earthquake environment where the Geogrid reinforced wall was damaged, and what we show in here is that there's a repair detail that can be adopted to repair the Geogrid. So it's going to be excavated out, replaced, and then connect the rest of the facing panel that is still structurally suitable to the zone of damage where a new set of panels would need to be constructed. And this slide here is just to indicate how many number of panels we need to be replaced, and panels that, in the case that we considered, can still be left without having to be removed. And then this slide relates that to the outcome of the analysis to show areas where those geogrids have been stressed to their ultimate limit in terms of tensile strength and strain, and how we would envisage that such repair will be undertaken. We did try to look at cost-benefit ratio of doing that, because now we are not, one would have to consider the whole life cost of between the upfront cost of use of reinforced concrete wing walls to the cheaper alternative of reinforced earth wing wall, having demonstrated that both would work and will perform similar function in terms of protecting the bridge. But for the reinforced earth alternative, the cost of repair will then have to be taken into account, which is what the numbers that we have on this list. I think it would be better to look at the summary. As an illustrative figure, we envisage that there will be, I mean, the 26K is not an absolute number is just to look at a number to say there will be a savings in material, a saving in program, which is not costed in this particular presentation. And there will also be the sustainability aspect of this in terms of the use of Geogrid and soil rather than concrete, which is got a much higher carbon footprint. Not going to go too much into the detail of the breakdown of this cost because these are all compared to fixed units, which would differ from bridge to bridge, but approximately this is showing that there will be substantial savings between the reinforced concrete option to the Geogrid reinforced option. Here we're talking about nearly a quarter of £1,000,000. But again, this is relative to the size of the bridge and the size of the damage zone that we considered in this particular study. But the bottom line is that there will be a substantial net savings between the two applications. It's estimated to be about 50% of that. Again, it's relative to the bridge that one would consider. But as an illustration, it's got cost benefit, and also it's got benefit in terms of carbon. Environmental assessment, there is a study that we're currently doing right now to these numbers here are based on a separate research that we did a few years ago with Tensar, where we look at the carbon footprint of the Geogrid elements as compared to reinforced concrete. This is currently, we said, about 57% in this study, but we are updating this right now based on more recent figures. That particular research is still ongoing. It may very well still be roughly about 57% that we're going to end up with, but I cannot give you an updated number on that until we finish the research. And that's the end of the presentation. Thank you. Questions?
Okay, thank you very much, Basil. I haven't got any questions in the chat. If you've got any questions, please put them in the chat. I think it would just be helpful for me. Thank you very much for that, Basil. Very interesting. I've not experienced myself at all on reinforced structures. So in terms of what the tensile material is and how it's constructed, that would be, if you're able to summarize that, that would be useful.
So I'll just go back to this, and I suppose something I missed out of that. Out of this research, so this research is now, the outcome of it has been presented to HS2 and the various design houses involved, and has been accepted. So this solution has been accepted as a suitable solution for use in high-speed environment. And with regards to your question, how this is built, so we have Geogrid layers that is built in sequence, and typically I can say I've got Peter Matthias from Tensar on the call, so might be able to provide a bit more detail on that. So we've got it's going to be built in layers. So you've got your Geogrid, probably about 400 to 500 mil layers, which is connected to the concrete panels, and then the resistance that the reinforced wall derived to support itself as you go up is now derived from the weight of soil on the Geogrid layer and the frictional resistance that is mobilized as that soil tries to move out. So it's pretty much based on friction. So load times the coefficient of friction on the material, and as you go up, your load increases and your coefficient of friction obviously remains constant, but that then supports the face of the structure as you build it upwards.
So how deep is this lump, that reinforced lump on the wing wall? Sorry if I put it like that.
That's a technical term.
Yeah.
Now, when you say how deep this is,
yeah, oh, there it is, 6 meters. I see.
Yeah, well, the structure itself, the retained height of the structure is about 8 meters.
Yeah.
So the structure is about 8 meters in retained height. The embedment here is only about 500 mil. We've got 0.47, and that's just one of the standard embedment detail. And what I meant by the sequential layering of the geogrid is actually shown here. So the dotted lines are the geogrid reinforcements connected to the concrete facing.
Okay, so when, if in the event, unfortunate event, there was a repair needed, you'd have to dig right back, I guess. And
yeah, so in the unfortunate event of a derailment, even for a reinforced concrete wing wall, such structure would have to be structurally inspected, and oftentimes there will have to be substantial repair. So we are talking about a train traveling at about 330 kilometers an hour. So there will be a whole raft of other inspections that would have to, to happen. But specifically in regards to the repair of the reinforced earth wall alternative, we expect that the entire geogrid within the damage zone will have to come out. So the yellow area here will have to be excavated out and then rebuilt back up.
Okay, thanks. Well, personally, I think I still haven't got any other questions, I'm afraid, Basil. But firstly, I think you've demonstrated that this is a really good sort of carbon reducing option. I hope that's been noted, because I think in terms of the cost and the amount of concrete that's been in there, it's a significant savings. Well, I see we actually, people are drifting off the session as also. I think no more questions. We'll call it a day there, so that I can say thank you to you and with the audience. And I personally found that very interesting in terms of sustainable. I'd like to, I mean, I would suggest you might be interested in that sustainable conference, which we would encourage perhaps some expansion of this. I think other use of reinforced assets, perhaps talk to Tensar and come along to the Bristol event in November. I think that would be good, where we can engage and have great discussion. Okay, well, if anyone else is able to unmute, we would like, I found it fascinating. I'd love to know more, actually, but I think we need to put it to a close because everyone's disappearing off now. So I'd like you to unmute if you could, and if anyone's able to, and I thank Basil with some applause as we can in front of our computers, please. Looks like one person is going to do it with me, so we'll thank you very much, Basil. There we are.